This is Dr. Shankaraiah from Department of Physics. In the last presentations, I have discussed about Module 4, that is magnetic and superconducting materials. Okay, so in this presentation, I am going to start the second part of the Module 4, which is superconducting materials. So I have completed the first part of Module 4, which is magnetic materials. So I am going to start the second part of Module 4, which is superconducting materials. So the first topics in superconducting materials are superconductivity and properties of superconductors. So this is a picture of Camerlin Onnes, who invented this superconductivity. Okay. So first we will start with introduction to superconductivity. Superconductivity is a state of matter exhibited usually at very low temperatures, where the resistivity of the materials drops to zero. Okay, superconductivity is a property or state of matter. Okay, so materials exhibit this superconductivity usually at very low temperatures. Only at very low temperatures materials exhibit this superconductivity, and the requirement is that the resistivity of the materials drops to zero. When the resistivity of the material drops to zero, only then the materials can exhibit the superconductivity, and that is only at very low temperatures. Okay, so the superconducting state is a state in which quantum mechanics operates on a macroscopic scale of the order of many atomic distances rather than the usual atomic or subatomic scale. In superconducting state, we can understand the superconducting state using quantum mechanics, where we use it on macroscopic scale. The superconducting state, okay, superconducting state is a state in which we can use quantum mechanics to understand its superconducting state on a macroscopic scale. Okay, the superconducting state is influenced by temperature, current, and magnetic field. We can change the superconducting state, or we can destroy the superconducting state. We can create the superconducting state by changing temperature, current, and magnetic field. Any one of these parameters. You can change temperature, you can make the material superconducting, or you can destroy the superconducting state to a normal state by changing the temperature. As well as you can use current or magnetic field to make a material superconducting, or to destroy the superconducting state and to make the material into a normal state. Okay. So there exist critical values for all these three parameters above which the material passes into a normal state. Okay, so all these three parameters, they have a critical values. That means that above certain value of temperature, the material loses its superconducting state and it will go to into a normal state. Similarly, current also, it has a critical value. So above some value of current, the superconducting state will be lost of the material, and it will go into a normal state. Similarly, magnetic field also has a critical value above which the material loses its superconducting state and it goes into a normal state. This phenomenon has many possible practical applications like transportation, transmission of power, and medicine. So superconductivity used in many applications are like transportation. We can use this superconducting property in transportation, where we can use maglev trains, and we can use in transmission of power transmission. If we have a room temperature superconductors, we can save so much of power. And we can also use these superconducting properties in medicine, where we use these superconducting materials in MRI scanning. Okay, so with this so let us go and discuss some more introduction to this superconductivity. Okay, so metals are good conductors or conductors of electricity. We all know that metals are good conductors of electricity as they contain a tremendous number of free electrons. Why metals are good conductors of electricity? Because they have so many number of free electrons, and because of those free electrons, these metals behave as very good conductors. The low resistance offered by them to the flow of current is attributed to the scattering of free electrons by vibrating ions of the lattice. So why do these metals have low resistance? The low resistance of these metals is because of the flow of current attributed to the scattering of free electrons by the lattice. So there are many electrons. We said that metals have tremendous number of free electrons, and the low resistance of metals is coming from the flow of current, which is attributed to the scattering of electrons. Okay, so there is very less scattering of the electrons in metals, and hence the low scattering of the electrons gives rise to the low resistance of metals. When temperature increases, the amplitude of these lattice vibrations increase and cause more scattering of electrons, leading to more resistance. So because of this low scattering metals, they are very good carriers of current. And when you increase the temperature, when the temperature increases, when we are increasing the temperature of these metals, the amplitude of the lattice vibrations increases and can cause more scattering, leading to more resistance. Okay, so if you increase the temperature, the lattice vibration, so we know that this way we can understand these metals through the theory of lattice vibrations, right? So when you increase the temperature, these atoms will vibrate, and the lattice amplitude of these lattice vibrations will increase, and it causes more scattering of these free electrons, and hence the resistance will also increase. Even at 0 Kelvin, metals offer finite resistance and is called residual resistance. We know that metals are good conductors because of free electrons and the scattering of these free electrons, right? So even when we are going to 0 Kelvin temperatures, we find these metals have small resistance. The resistance is not zero. The resistance of metals is not zero. The metals have finite resistance even at 0 Kelvin. And this finite resistance at 0 Kelvin of metals is coming because of the scattering of free electrons. Okay, and this is the finite resistance of metals at 0 Kelvin temperature is attributed to the scattering of electrons by impurities and crystal defects present in the material. Whatever material we are using as a metal, if the material has any impurities or any defects, those defects or impurities will give rise to more scattering of the electrons, and hence you have finite resistance even at absolute 0 Kelvin. Okay, so here we understood that even though metals are good conductors of electricity, even though you are taking or lowering the temperature to absolute 0 Kelvin, you don't find the resistivity of the metals going down to 0. You find that there is a finite resistance even at 0 Kelvin temperature in metals. The finite resistance is called residual resistance, and reason for this finite resistance in metals is understood through the presence of impurities or defects in metals. The variation of resistivity of normal metals with temperature is shown in figure. So you can see here in this picture, so the y-axis is electrical resistivity and the x-axis is temperature. Okay, so the normal metal, as you see the resistance as you decrease so this is the direction of decreasing temperature. So as I decrease the temperature, the resistance, the y-axis is electrical resistivity. So the resistance is decreasing, and it decreased to a finite value even though I have decreased the temperature to absolute 0 Kelvin, right? So even though I decrease the temperature to 0 Kelvin, the resistivity dropped to a finite value, which is called residual resistance. Okay, so at Hannes Camerlin Onnes, okay, Camerlin Onnes was verifying the behavior of metals temperatures in 1911. Okay, so Camerlin Onnes is a scientist who was studying the resistance of metals. He want to understand how the resistance decreases with temperature. So he is studying the resistance of metals in the year of 1911, and he discovered that the electrical resistance of highly purified mercury dropped abruptly to 0 at a temperature of 4.15 Kelvin. As scientist Camerlin Onnes studying trying to understand or studying the behavior of metals, particularly looking at the resistivity of the metals to understand how the resistivity of these metals will change or decrease with decreasing temperature. And he discovered that in a material which is highly purified, and that is mercury. So in a highly purified mercury, he discovered that the electrical resistivity is dropped abruptly to 0 at a temperature of 4.15 Kelvin. We all know that the metals also, even you reduce the temperature of these metals to 0 Kelvin, we find there is some residual resistance. There is some residual resistance even at absolute 0 Kelvin. But Camerlin Honest found that in a purified mercury, he found that the resistivity dropped to 0. The resistivity dropped to 0 at a temperature of 4.15 Kelvin. So this is the curve of highly purified mercury. So this is the curve. So as the temperature decreasing, the resistivity also decreased. But at a temperature which is called TC, critical temperature, the resistivity suddenly abruptly decreased to zero resistivity. Okay, so this temperature is called critical temperature. So this material, the material whose resistance dropped to 0 below a temperature called critical temperature, that material is called as superconductor. And the phenomenon in which the resistivity of a material drops abruptly to 0 at a particular temperature called superconductivity. Okay, so the sudden drop in resistivity was quite unexpected. We do not expect, we have looked at the resistivity of metals, and we found that resistivity is not 0. It has some finite resistance even at 0 Kelvin. So we don't expect that the resistivity will go to 0. So that is why the sudden drop in resistivity was quite unexpected, and Honest recognized it to be an entirely new phenomenon. So this is something new he observed, and he thinks that this new phenomenon, and he named this new phenomenon as superconductivity, because conductors are finite resistance at 0 Kelvin, but these materials has 0 resistance below a certain temperature, and hence he named as superconductors, because the resistivity is dropped to 0 below a certain temperature. Okay, so that is why the name superconductivity or superconductors came. Honest also found that the transition was reversible. So as you decrease the temperature, this is the direction of decreasing temperature. As you decrease the temperature, the material is becoming superconductor from normal state to superconducting state. But as you increase the temperature for 0 Kelvin, again the material will go from superconducting state to a normal state. So the transition of superconducting state to normal state is a reversible transition. That is what Honest observed in his experiment. When he heated above the transition temperature of 4.15 Kelvin, mercury regained its resistivity, and this phenomenon he named it as superconductivity. So he found that the resistivity of this highly purified mercury dropped to 0 below 4.15 Kelvin, and when he increased from 0 Kelvin, again he found that the resistivity, thus this material, highly purified mercury, again regained its resistivity above 4.15 Kelvin. So this superconducting transition is a reversible transition, and this phenomenon in which the resistivity of a material drops to 0 abruptly below a certain temperature is called as superconductivity. Okay. Subsequently, the superconductivity was discovered in lead, zinc, aluminum, and other metals and alloys. So first, Camerlin Honest was discovered this superconductivity in highly purified mercury, but later on this superconductivity was discovered in other materials, alloys, and other metals. Okay, superconductivity is the phenomenon in which electrical resistivity of electrical resistance of materials suddenly disappears below a certain temperature. So you can define what is superconductivity. So you can define from here, superconductivity is a phenomenon in which electrical resistance of materials suddenly disappears below a certain temperature, and this phenomenon is called superconductivity. And the materials that exhibit this superconductivity are called superconductors. So if you have to define what is superconductivity or what is a superconductor, you can use this statement to define superconductivity and also superconductors. So this is the discussion or introduction to superconductivity. What is superconductivity? Who discovered the superconductivity, and what are superconductors, right? So now we are going to discuss about some properties of superconductors. So superconductors exhibit many unusual and interesting properties. Superconductors exhibit many unusual and interesting properties. So the first one is zero electrical resistance, right? So superconductors exhibit this phenomenon or zero electrical resistance. This property called zero electrical resistance. A superconductor is characterized by zero electrical resistivity. Yes, a superconducting ring is taken in normal state. So to understand why there is there a zero electrical resistance in a superconductor, we are going to take a superconducting ring. This superconducting ring is in the normal state. That means it is at high temperatures. At high temperature, at T greater than Tc, we know that at T greater than Tc, the material will be in normal state. There is no superconducting state. Only when T less than Tc, you have superconducting state, and when T greater than Tc, normal state. Okay, so this is superconducting state, and this is normal state. Okay. So first, to understand the zero electrical resistance of a superconducting material, we are taking a superconducting ring which is in the normal state and kept in a magnetic field, and it is cooled below the critical temperature. We have taken a superconducting ring, and we are maintaining the temperature of the superconducting ring T greater than Tc. So this superconducting ring is in normal state. Then we have placed this superconducting ring in the presence of magnetic field. We have placed it in the presence of magnetic field, and we have cooled this superconducting material so that it goes to T less than Tc. Okay. Then we find that this ring will now go from superconducting normal state to superconducting state. As we have cooled this material below Tc, this material will go from normal state to superconducting state. When the external magnetic field is switched off, a current is induced in the magnetic field. So to understand the zero electrical resistance of this superconducting material, we have taken a material which can become superconductor, right? And then we have taken that material in the form of a closed ring, and then we have maintained the temperature T greater than Tc so that it will be in the normal state. Then we have placed this ring in the presence of magnetic field. This ring is in closed ring, right? It's in the closed loop. So we have placed this closed ring in the presence of magnetic field, and then we have cooled this material so that it goes to T less than Tc. When we cool this material, then this material will go from normal state to superconducting state. Okay. Once the material goes into superconducting state, then we switch off the magnetic field. By changing the magnetic field, there will be a current that will be induced in this ring, right? Changing magnetic field can induce current in a closed loop, and hence when we switch off this magnetic field, current will be induced in this ring. If the ring had a finite resistance R, the current circulating in the ring would decreases according to the equation. So now, because when we switch off this magnetic field, this changing magnetic field induces current in the closed loop, and then the current circulating in this ring would be having this formula. So that is I of t. So t is time. So the current I of t is equal to I of 0 and exponential to minus RT by L, where L is inductance of the ring. Okay. So I of t. So the current in the superconducting ring will vary with the time as I of 0 into e power minus RT by L, where R is resistance, T is time, and L is inductance of the ring. So the decay current is monitored by a change in the magnetic flux through a test coil held close to the superconducting ring. Now we know that there is a current that is flowing in the superconducting ring. So if this material has zero resistance, then the current that is induced in this ring will flow forever, right? So if we want to see whether the resistance is zero or not, or the current that is circulating in this coil is forever, it is of same strength, we are going to add a test coil to this. We are going to add a test coil to this closed superconducting ring, and we are going to observe the magnetic flux lines that are induced because of the current that is flowing in this closed loop. Okay, if there is no change in the magnetic flux of the superconducting ring, that it will induce an EMF in the test coil, and then we will find that if there is no change in the EMF in the test coil, we will find that the current that is circulating in the superconducting ring has zero resistance. Because of that zero resistance, we will find that there is no change in the magnetic flux lines that are introduced because of the current flowing in the superconducting ring, and hence the EMF that is produced because of this magnetic flux has no change. Okay, so that is from these experiment we can conclude that the resistivity of the superconducting materials, it can be taken as zero. Okay, so that is the first property of superconducting material, which is zero electrical resistance. The second property of superconductors is persistent current. So in the first property, while understanding the first property, we found that the current that is induced in the superconducting material is flowing forever without losing its strength. Okay, so that is what is called persistent current. Okay, so let us see about this persistent current. Once a current is started in a closed loop of superconducting material, it will continue to keep flowing. Okay, so once we induce or introduce a current in the superconducting material, it will continue and it will keep flowing of its own accord around the loop as long as the loop is held below the critical temperature. As long as we maintain the temperature T less than critical temperature, as long as the material is in the superconducting state, the current that is introduced in the ring will flow forever without losing its strength. Okay, so such a steady current which flows without losing or diminishing in strength is called persistent current. Okay, so persistent current is a current that is introduced in the superconducting material, introduced in the ring which is in the superconducting state. Okay, as long as the temperature is maintained T less than Tc, this current will flow forever without diminishing or without losing in strength, and such a steady current is called as persistent current. The persistent current does not need external power to maintain it because there is no resistance. The resistance is zero, and hence there do not exist any power losses. There are no power losses because resistance is totally zero. So there are no power losses. The power losses are also zero because the resistance is zero. Calculations show that once the current flow is initiated in a superconducting material, it persists for more than 10 power 5 years. That means 1 lakh years. If we have a superconducting material which is in the superconducting state, that is possible only if we maintain the temperature T less than Tc. Then if we introduce a current in the superconducting material, it will flow forever in that superconducting ring up to 1 lakh years. Okay, so that is because of the zero resistance of this superconducting material. Okay, so this current, that's a steady current which will not lose its strength and it flow forever, or around, you can mention it is a 1 lakh years, and such a steady state current which flows without diminishing in strength is called a persistent current. So persistent current is one of the most important properties of a superconductor. Superconductor coils with persistent current flowing through them produce magnetic fields and can therefore act as magnets. Once the current is introduced in the superconductor, this current will flow for 1 lakh years, and when the current carrying conductor can generate magnetic field, and you can use this superconducting ring as a magnet. Okay, such a superconducting magnet does not require power supplies to maintain its magnetic field because it is not losing its strength because the resistance is zero. So we don't need to worry about the power supply because resistance is zero and current flowing in the ring will remain forever up to 1 lakh years. So there is no need to maintain power for this superconducting ring, which we can use it as a magnet. So that is the second property of a superconductor, which is called persistent current. Coming to the third property, which is critical temperature. Right? When a superconducting material is cooled below a certain temperature, when a superconducting material is cooled below a certain temperature, it goes into the superconducting state from the normal state. Right? So this is what we discussed in the beginning. The temperature at which a material in normal state goes into the superconducting state is called as critical temperature. So different materials have different critical temperature. So there are, as we discussed, there are many superconducting materials: lead, zinc, mercury, metals and alloys. So each material has its own critical temperature. All the materials do not have same critical temperature. Each material has its own critical temperature. And the transition is reversible, so that we discussed. When the temperature of the material is increased above Tc, it passes into the normal state. The transition is a thermodynamic phase transition. So there are two phases. The first phase is superconducting phase and the other phase is normal phase. So this superconducting transition from normal state to superconducting state by changing temperature, this transition is a thermodynamic transition because it is there is a change from one phase to another phase. These two phases are normal state is one phase and superconducting state is another phase. Okay, so critical temperature, we defined it as a temperature below which the material will become superconducting and above which the material goes into normal state from superconducting state. So the temperature which is changing the material from one state to another state or one phase to another phase is called as critical temperature, and different materials have different critical temperatures. Just as the order in the arrangement of atoms increases at the transition of a material from liquid to solid state, a rearrangement of conduction electrons takes place, leading to an increase in the order at the transition from normal to superconducting state. So to understand the phase transition, how a material goes from superconducting state to normal state as we increase the temperature, or how a material goes from normal state to superconducting state as we decrease the temperature. To understand this thermodynamic phase transition, you can think of how liquid freezes into a solid, or how a solid will become a liquid as you increase the temperature. We know that ice can melt when you put in sun, right? So as we are increasing the temperature, ice, which is a solid, will go into a liquid, right? Water. So how do we understand this liquid to solid phase transition? We can think of that solid is a material where all the atoms are sitting rigidly, but as we increase the temperature, these atoms are, now the distance between the atoms is increasing and it is going into a liquid state. So there is a rearrangement of atoms. Okay, so there is a rearrangement of atoms when ice melting into a liquid, or solids when a solid is changing into a liquid and changing temperature. Similarly, here also there is a rearrangement of conduction electrons that takes place, leading to an increase in the order at the transition from normal state to conduction state. Okay, so these in these superconducting materials also there is a increase in order as you go from normal state to superconducting state. That means as you decrease your temperature, these conduction electrons will be arranged in a order, so that there is increase in order as we go from normal state to superconducting state. So the superconducting transition is sharp for a chemically pure and structurally perfect specimen, while the transition range is broad for specimens which are structurally imperfect, which can contain impurities. If you can prepare a material, for example mercury, if you can prepare the mercury with chemically pure, very pure mercury, then the transition is very sharp. You will see at a particular temperature of 4.15 Kelvin, this mercury will go from normal state to superconducting state. But if you are not able to prepare a very pure material, then the transition will be broad. That means there will be a broad range of temperature in which this material can go from normal state to superconducting state. Okay, yeah. So that is the third property of the superconductors, which is critical temperature. Next, we are going to discuss about the fourth property of this superconductor, which is critical magnetic field. Okay. So superconducting state depends on the strength of the magnetic field in which the material is placed. Okay, so superconducting state depends on the strength of the magnetic field in which we are placing the material. Superconductivity vanishes if a sufficiently strong magnetic field is applied. Okay, superconductivity can be destroyed if you apply a large magnetic fields. The minimum magnetic field which is necessary to regain the normal resistivity is called critical magnetic field. Okay. Even though we are maintaining the temperature T less than Tc, we can destroy the superconductivity, the property of superconductivity, by increasing or by applying high magnetic fields. Okay. So there is a critical magnetic field below which the material will be in superconducting state. If you apply, if the field H is greater than Hc, then you will find the material will be going from superconducting state to normal state. So if H is less than Hc, Hc is the critical field, then the material will be in superconducting state. If H is greater than Hc, the material will go from superconducting state to normal state. Okay, so that is normal state. So when the applied magnetic field exceeds the critical value Hc, the superconducting state is destroyed and the material goes into the normal state. Okay. So when we place the material in the presence of magnetic field, we can destroy the property of superconductivity by increasing the applied magnetic field above a critical value. Okay. So there is a critical magnetic field that you can apply to the material. So that if you want to destroy the superconducting state, you apply more, you apply a field greater than Hc. If you want to remain, if you want the material to be in superconducting state, you apply a field less than Hc. Okay. So we are defining there is a critical magnetic field below which the material will be in superconducting state, above which the material loses its superconducting state and it goes into normal state. The value of Hc, which is critical magnetic field, varies with temperature. Okay. So here is the variation of critical magnetic field H with respect to temperature. So as you increase your temperature, the magnetic field will also decreases. Okay. So yeah, at T less than Tc, in the absence of magnetic field, the material is in superconducting state. We know that when T less than Tc, there is no magnetic field. That means H is 0. In the absence of magnetic field, and only when T less than Tc, the material will be in superconducting state. Right? So when a magnetic field H is applied, as its strength reaches the value of Hc, the superconductivity in the material disappears. Even though you are below Tc, even though you are below Tc, we are below Tc, so that means the material is in superconducting. Now field is 0. But even though T is less than Tc, as you increase your applied magnetic field, the material can lose its superconducting state. Okay. So this is the line that separates the superconducting state. So all this is a superconducting state, and above this there is no superconducting state. So it will be in normal state. Okay. Suppose I have the material at this temperature. So this is the temperature where I am, and the field is 0, for example, and T is very less than Tc, so the material is in superconducting state. Now I increase the applied magnetic field to this material. As I increase the magnetic field, as I increase the magnetic field, this material will go from superconducting state to normal state at H greater than this Hc. Okay. So this is the variation of applied magnetic field with temperature. So yeah, at any temperature T less than Tc, the material remains in the superconducting state until H is equal to Hc. At any temperature T less than Tc, the material will remain in superconducting state until H less than Hc. As long as T less than Tc, H less than Hc, the material will be in superconducting state. When H greater than Hc, the critical value, the material will go immediately into normal state even though T is less than Tc. So we can destroy this superconducting state by increasing the magnetic field, that is H greater than Hc. We can destroy the superconducting state even though the temperature T is less than Tc. Okay. So the critical field required to destroy the superconducting state decreases progressively with increasing temperature. Okay, so that is what we have seen here. The critical magnetic field required to destroy the superconducting state increases progressively with increasing temperature. So dependence of critical field on temperature is governed by this equation. So this is the equation. So that is Hc of T. So that is the critical field with temperature. So how does the critical field vary with temperature? So Hc of T is equal to Hc of 0 at T is equal to 0. You have a critical field, that is Hc0, multiplied with 1 minus T by Tc whole square. Okay. So this is the variation of applied magnetic field, okay, with temperature. T is temperature, Tc is the critical temperature. So Hc of T is Hc of 0 into 1 minus T by Tc whole square. So this is the variation of critical field, where Hc of 0 is the field, critical field at 0 Kelvin. Okay. So this is the fourth property of superconductors, which is critical magnetic field. Okay. So the fifth property of these superconductors is critical current density. The critical magnetic field required to destroy the superconductivity need not be necessarily applied externally. Okay, so very important point. The critical magnetic field required to destroy the superconductivity need not be necessarily applied externally. If you want to destroy the superconducting state, you don't need to apply external magnetic field. We don't need to take the material and put it in the presence of magnetic field. Without applying the external magnetic field also, we can destroy the superconducting state. How? Okay, so that is what we will see. An electric current flowing through superconducting material itself may produce magnetic field of required strength. We know that once we introduce the current into a superconducting ring, the current will flow forever to us, at least for 1 lakh years, forever, without diminishing in strength. Okay, such a current is called persistent current. So as the current flowing without any resistance, with zero resistance, the current that is flowing in this material, superconducting ring, can itself produce magnetic field. And if the produced magnetic field, the magnetic field that is produced because of the current flowing in the superconducting ring is greater than a critical field, then the superconducting state can be destroyed and the material will go into a normal state. Okay. Thus, if a superconducting ring carries a current I, it gives rise to its own magnetic field. Okay. As the current increases to a critical value IC, the associated magnetic field increases to a value HC, and the superconductivity disappears. If the current flowing in the superconducting ring reaches to a critical value, IC, the critical current. If the value reaches to a critical current, then the magnetic field that is produced because of the current flowing in the superconducting ring will also increases to a value HC. And when the magnetic field greater than this HC critical magnetic field, then the material loses its superconductivity and it will go into a normal state. The maximum current density at which superconductivity disappears is called the critical current density. Okay, so not only we destroy the superconductivity state by putting the material in an external magnetic field, we can destroy the superconducting state by increasing the current in the superconducting ring, because the current that is flowing in the superconducting ring itself can generate magnetic field. We know that magnetic field is generated by the current flow, right? So as the current flowing in this superconducting ring increases to a critical value IC or critical current density JC, then the magnetic field that is produced by this current will also increases, and if it crosses a critical magnetic field HC, then the material loses its superconductivity and it will go into a normal state. The maximum current that a superconductor can carry decreases as the temperature is raised. So the maximum current that a superconductor can carry decreases as the temperature is raised. As we increase the temperature, the superconductor cannot carry more current. Okay, so the maximum current that a superconductor carries decreases as we increase the temperature and falls to zero at transition temperature. As we start increasing temperature from zero, then the current that can carried by the superconductor will also decreases, and at a temperature Tc, the current that can be carried by this superconductor will go to zero. Okay, because now the superconductor, the material is going to lose its superconducting state and it is going to become a normal state, and hence the current that can carry by this material will be zero. Since the critical current falls with temperature, the critical magnetic field, since we know that the critical current falls with temperature, the critical magnetic field will also decrease as the transition temperature is approached. As the critical current decreases with the increasing magnetic field, we find that the critical magnetic field will also decreases as we reach this transition temperature. So this is the variation of critical current density and magnetic field and temperature. So all these three parameters we can see, and this is the curve in which you have the superconducting state. Inside this you have the superconducting state, and above this curve above this surface there is no superconducting state. You have normal state above this surface, above these values. Okay, so the variation of critical current density Jc and critical magnetic field Hc with temperature is given in this picture. The variation of critical current density and the variation of critical magnetic field with temperature, both these parameters with temperature, variation of temperature is given in this picture. So this is about critical current density. So the last property of a superconductor is perfect diamagnetism, and this perfect diamagnetism is also called as Meissner effect. Okay, so Meissner effect is also called as perfect diamagnetism. So to understand this perfect diamagnetism, in 1933 Meissner and Hossenfeld found that when superconductors are cooled below their critical temperature in the presence of magnet, it's important to note, superconductors are cooled below their critical temperature in the presence of magnetic field, the magnetic flux is expelled from the interior of the specimen and the superconductor becomes a perfect diamagnetic material, and this phenomenon is known as Meissner effect. So we have taken a mercury for example, and we are cooling this mercury in the presence of material, in the presence of magnetic field. So we have magnetic field. So this is, we are applying the magnetic field, and this is the material, right? So as we cool this material below Tc, okay, as we are above temperature, we are at T greater than Tc, even though there is a field H greater than Hc or T greater than Tc, we will find the applied magnetic field will penetrate to this material, or the magnetic flux lines will pass to the semiconductor material, because at T greater than Tc the material is in the normal state. But as T less than Tc or H less than Hc, we will find that as we are cooling the material below Tc in the presence of magnetic field, when we reach the temperature Tc, the magnetic flux lines will be repelled by this superconducting material. So, okay, and this property is called as Meissner effect. The material, as we cool the superconducting material in the presence of magnetic field at a temperature, as we reach the temperature T equal to Tc, the critical transition temperature, we find that the magnetic field is expelled from the interior of this superconducting material. Okay, and this phenomenon is called as Meissner effect, and the expulsion of the external magnetic field by a material is called diamagnetic. So the only diamagnetic material can exhibit this phenomenon of Meissner effect. Okay, so diamagnetic materials in general repel the applied magnetic fields. Okay, now we find this superconductor is going to exhibit this perfect diamagnetic behavior, as it is also repelling the applied magnetic field when T is less than Tc, and this property is called as Meissner effect or perfect diamagnetism. Okay, so you can understand this perfect diamagnetism or Meissner effect from these pictures. As when T greater than Tc, the magnetic field is penetrated through this. So this is the specimen, right? So the magnetic flux lines are passing through the material, right? So when T greater than Tc. When T less than Tc, you clearly see the magnetic flux lines are expelled from the interior of the specimen. No flux lines passing through the material, okay? So the expulsion of the applied external magnetic field is a property of diamagnetic material, and this superconducting material will exhibit this perfect diamagnetism when T less than Tc. Meissner and Ostenfeld found that as the temperature of the specimen is lower to Tc, the magnetic flux is suddenly and completely expelled from it. So the flux expulsion continues until T greater than Tc. As the temperature is less than Tc, the magnetic flux lines will be expelled from the interior of the specimen, and this effect is also reversible. Okay, that means as we are starting from the 0 Kelvin, as we increase slowly the temperature, we will find that up to T is less than Tc, we will find the flux lines will be expelled, and when T reaches Tc, we will find the magnetic flux lines will pass through the material. Okay, so that is why we are saying that this Meissner effect is reversible. When the temperature is raised from below Tc, the flux suddenly penetrates the specimen at T is equal to Tc, and the material returns to the normal state. So when T less than Tc, the material is in superconducting state and it expels the applied magnetic field, and this is Meissner effect. When T is greater than or equal to Tc, now there is no expulsion of the external magnetic field. The magnetic flux lines pass through the material, and this material the specimen will go from superconducting state to normal state. The magnetic induction inside the specimen is given by this formula. So the magnetic induction, we have discussed about magnetic field induction or magnetic flux density, which is denoted by B. Okay, so B is equal to mu naught into H plus M. This is the formula where H is the applied magnetic field and M is the magnetization that is produced inside a material. And this we can write H, we can write M as chi into H. So when we place this chi H in this formula, okay, so this will become mu naught into H plus chi into H. Okay, so you can take out the H common. So when you take out common, mu naught into 1 plus chi into H. So that is what I have here. So B is equal to mu naught into 1 plus chi into H, because this we are writing this magnetization M. We know that applied the magnetic magnetization of a material is directly proportional to the applied magnetic field, or M is equal to chi into H, where chi is susceptible. So I have replaced this magnetization M by susceptibility into applied magnetic field, and when I take out this H common, I found that mu naught B is equal to mu naught into 1 plus chi into H. So where H is the applied magnetic field and M is the magnetization of a material. Okay, so this is the formula for the magnetic field induction inside a specimen. Okay, now we are going to see that at T less than Tc, B is equal to 0, and therefore at T less than Tc, B is equal to 0, because all the magnetic flux lines are expelled. At T less than Tc, you see, all the magnetic flux lines are expelled. No magnetic flux lines is penetrated through the material, so the magnetic induction is 0. Because of this, mu naught into H plus M is 0. That means mu naught into H plus M is 0 means mu naught is equal to 0 and H plus M is equal to 0. Okay, H plus M is equal to 0 is nothing but M is equal to minus H, or M by H, which is equal to chi, is equal to minus 1. Okay, the specimen is therefore diamagnetic, and the state in which the magnetization cancels the external magnetic field completely is referred to as perfect diamagnetism. So there's two mutually independent properties. Zero resistivity and perfect diamagnetism are the essential properties that characterize a superconducting state. Sometimes they will ask you to prove that the superconducting for T less than Tc, superconductors exhibit, or the susceptibility of superconductivity is -1, or the superconductor becomes a perfect diamagnetic material. So then you can start from this formula of B is equal to mu naught into H plus M, and then you can write this equation like mu naught into 1 plus chi into H, and when T less than Tc, so it's very important, when T less than Tc, all the magnetic flux lines are expelled. So that is the reason why B is equal to 0. Because B is equal to 0, mu naught into 1 plus chi into H is also 0, or mu naught into H plus M is also 0. So mu naught into H plus M is equal to 0 means H is equal to minus M, or M by H is equal to minus M, but M by H, we know that M by H is equal to chi, susceptibility. So that is how we prove that susceptibility is minus 1. So this is a property of diamagnetic material. So susceptibility is negative for diamagnetic material. So by taking these equations and proving that chi is equal to minus 1, we are saying that the superconducting material is going to behave like a perfect diamagnetic material when T less than Tc, right? Yeah. So this is the last property of a superconducting material. Okay. So some applications of Meissner effect here. The Meissner effect is the standard test used to conclusively prove whether a material is superconductor or not. So you can use the Meissner effect because these mutually are independent properties, that is Meissner effect and zero resistance. These two properties are the important properties that characterize the superconducting state. So Meissner effect can be used to find whether a particular material is superconducting or not. A material in superconducting state is a perfect diamagnet and hence strongly repels external magnetic fields. A smaller magnet repelled by a bigger superconductor hovers in air, and this is known as levitation effect. Okay, so if you have a superconductor and you have small magnet on the top of the superconductor, the superconductor will expel the magnet, right? So that is the reason why this magnet which is on the top of this big superconducting material will hover in air, and this is called as levitation effect. So generally it will flow in air, right? So for example, let me show here. So I have a large superconducting material. This is superconducting material, and this is a very small magnet. So this is a magnetic material. So because when T less than Tc, this superconducting material is going to repel the magnets, applied external magnet. So that is the reason why it is going to repel this magnet. So hence it will float in the air. This small magnet will float in air, and this is known as levitation effect. Okay, so in a similar way, a small chip of superconducting material hangs onto a bigger magnet, and this effect is known as suspension effect. And if you have a small superconducting material, or if you have a small chip of superconducting material and it hangs onto a bigger magnet, and this is known as suspension effect. So you can have, if you have a magnet and superconducting materials, so you can make them, one is big, one is small. So you can see these two effects, which is levitation effect and suspension effect. Okay, so this levitation effect is utilized in the operation of maglev trains, which will float in air. Okay, so these are some applications of Meissner effect. Okay, so these are the references that I used in this presentation. And to summarize, so in this presentation I have discussed about the introduction to, first I have discussed about introduction to superconductivity, so in which I have discussed what is superconductivity and what is a superconductor, and what are the materials that exhibit superconductivity, what are the critical temperatures, okay, and who invented this phenomenon of superconductivity. Then I have discussed about the properties of superconductors. So I have discussed about 6 properties of superconductors, starting from zero electrical resistance. So the first property I have discussed about is zero electrical resistance, right? And then I have discussed about persistent current. The second property I have discussed about is persistent current, and third property I have discussed about is critical temperature Tc, and the fourth one is critical magnetic field. Okay, and the fifth one I have discussed, the fifth property I have discussed is critical current density. So there is a critical current, and the sixth one is perfect diamagnetism. or Meissner effect. Perfect magnetism or Meissner effect. Okay, so that is what I have discussed in this presentation, and I am ending the presentation here, and in the next presentation we will discuss the next topic in superconductivity. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.